Hi, Yuri's here. Welcome to the video on box plots. A box plot is a powerful type of data display which is useful already with a sample size of only 5 observations. And in this video we'll explore all aspects of the box plot, starting with a single value, the median, progressing through the simplest box plot possible, and finishing with a notched box-violin plot with 2 types of confidence intervals and statistical groups comparison. So at the end of this video, you'll be able to understand every little detail about this plot. As always, let's start with a simple example of data. There are 7 days in a week. 3 first days are the heaviest because we have to work, while the last 3 days of the week are the easiest because we approach and enjoy the weekend. Thursday is in the middle of the week and is neither heavy nor easy. It's just central. And that's exactly what the median is, a central value or the value in the middle. This means that there are exactly 50% of days before the median and 50% of days after the median. If we describe our weekdays in terms of numbers, day number 4 would be the median. And it doesn't matter how different or strange the numbers are, if they are ordered, the median is always in the middle. You may have noticed that 7 is an uneven number, which makes it easy to pick the median. What if we have 8 days, which is even? Well, you've guessed it, we just take the average of 2 numbers in the middle. Now, the left 50% of the data can also be split in half, so that 2 becomes the median of the left half of the data. This splits 50% into 2 times 25%, or 2 quarters of the data, where the line in between the first and the second quarters splits the whole dataset into 2 parts. 25% on the left and 75% on the right. Separating the first quarter from the whole dataset gave this line its name, the first quartile. Similarly, the median on the right half of the data is 6. And the line which has 3 quarters of data on its left and 1 quarter on the right is called the third quartile. Since our median has 2 quarters of data on its left, it can actually be called a second quartile. This name makes total sense, and it increases understanding of the box plot, but it's somehow rarely used. Most often, the first and the third quartiles are shown as Q1 and Q3, and they are always connected by lines. So that if we connect the quartiles and remove some unnecessary details, we'll get a box, which contains 50% of the data and is responsible for the name of the box plot. Such horizontal box plot beautifully shows how the median and the quartiles originate from data. But most of the time, box plots are displayed vertically. Here, the thick red horizontal line in the middle of the box is the median, which divides all data in half and also the data inside of the box in half, so that both sub-boxes have 25% of the data, even if they look completely uneven. The first quartile, or Q1, is the lowest horizontal line or hinge of the box, which, as we just learned, is greater than 25% of data and smaller than the other 75% of the data. It is also known as the lower quartile. The third quartile, or Q3, is the highest horizontal line or hinge of the box, and it is larger than 75% of the data and smaller than the remaining 25% of the data. It is also known as the upper quartile. Box length also provides useful information because the box contains 50% of the values. Since these 50% of the values range from the third to the first quartile, the length of the box is often called interquartile range, or IQR. So the interquartile range is the distance between the upper and the lower quartiles. Whiskers show data variability outside of the box, with the maximum sitting on the end of the highest whisker, which is often called 95th percentile. Maximum is the largest data point excluding any outliers. And the minimum sitting on the end of the lowest whisker, often called 5th percentile. Minimum is the lowest point excluding any outliers. So you see that every box and whisker plot displays the so-called 5-number summary of a particular sample. The 5-number summary contains the maximum, the third quartile, the median, the first quartile, and the minimum. The numbers on the vertical axis are usually displayed as points. The interquartile range is one of the most interesting numbers here. Despite the fact that it does not include the whiskers, it determines how long can whiskers be. By the way, are both whiskers always equally big and symmetric? The answer is no. How long should whiskers be? Well, a whisker is drawn up to the largest observed point from the dataset. So if the maximum is higher, the whisker can be longer. But how long can it be? Infinite? The answer is again no. Only 1.5 times the interquartile range. But what if a data point goes beyond this distance? You've guessed it, such data point becomes an outlier. Similarly, a distance of 1.5 times the interquartile range below the lower quartile contains the minimum data point. Are all data points behind this distance outliers? Actually not. If this distance surpasses 3 times the interquartile range, the point becomes extreme and should definitely be excluded from the dataset. But what about outliers? Should they always be excluded? It depends. Sometimes outliers are the most exciting data and delivers valuable insights. Thus, we need to understand the reason for the data point being an outlier before removing it. Let's have a look at an example of data and construct the box plot around it. How many hours a week do people usually watch Netflix? I asked 16 people. Most of them watch Netflix for 4 hours a week. These are approximately 4 episodes of a TV show. But when I thought about my Netflix habits and habits of my friends, the picture shifted towards 5 hours a week. It's kind of a lot, but I thought it's okay because I was sure I put the same effort into learning statistics. However, after being a bit more honest to myself, I realized that I spent much more time on Netflix than on learning. As you can see, the data on the left is distributed a bit differently than the data on the right, which can be shown with a smooth line on the top of the data. And in order to emphasize this difference even more, we could mirror the data and its distribution on the other side of the axis. Since the distribution curve shows the same as the data, we can actually remove the points in order to declutter our plot without losing any information. This would leave us with a violin plot, which aims to show the distribution of the data, whether it is normal or skewed, and to emphasize where the most of the data are, namely at the widest part of the violin. Interestingly, the box plot with its 5-number summary and the violin plot with its distribution are often shown together in the form of the elegant and very informative box-violin plot, which not only tells us a lot about each of the samples, but also allows us to compare them and see whether they are significantly different or not. But how do we compare two samples? Well, we can start with comparing their medians. but comparing only two numbers is certainly not enough to be confident about whether medians are really different. Thus, we need some kind of measure of certainty or measure of confidence about our medians. Such measure of confidence are actually the confidence intervals of the medians. Let's calculate them step by step. We'll start with something we already know, the interquartile range, which is the difference between the third and the first quartiles. We then multiply the interquartile range by 1.57 and divide the whole by square root of the number of observations in a sample. Adding and subtracting this whole expression to the median would give us the notch, which shows the approximate 95% confidence intervals of the median. So if we plug in the numbers 4 for the median, 6 and 2 for the quartiles, and 6 and 4n, and then simplify the equation, we'll finish up with the two numbers which are equally far away from the median. The first one is 5.57 and the second one is 2.43. The notches are usually displayed as a narrowing of the box around the median. You have most likely seen the notches displayed in this way before, but now you know exactly how they originate. Small sample sizes often result into larger confidence intervals than the box itself. In this case, it is not recommended to take such confidence intervals seriously. Good statistical programs, for example R, will even warn you about this. Thus, it's recommended to always provide the sample size and avoiding notches unless they fall entirely within the interquartile range. So how are the notches useful? Well, in general, if notches of neighboring box plots don't overlap, there is a strong evidence that samples significantly differ. We can use this in informal discussions or for gaining intuition about our data. However, we need to conduct a proper statistical test to be sure. Similarly, if notches of neighboring box plots do overlap, there is a strong evidence that samples don't differ. It's also often useful to display the average on the box plot, because it helps to visually estimate the normality or skewness of the distribution. Particularly, if the average is not far away from the median, the data is most likely normally distributed. However, if average is far away from the median, such data would most likely be skewed. The means can also be extended with 95% confident intervals in order to communicate more information about samples in roughly the same amount of space. So if we put together all we have learned so far, we'll end up with a pretty informative plot, which shows the box plots with 5-number summary, the notches showing 95% confidence intervals for the medians, the means with 95% confidence intervals, and the violin plots displaying the distribution. Now let's have a look at the real-world data and build our box plots around it from scratch, step by step. Here we can see a salary of two different working groups. On the left are industrial or factory workers, and on the right are the IT people or information technology guys. My very first trick in understanding the data is to always visualize it. We see that IT people earn kind of more, but we can't say for sure from the data alone, so we need some numbers for it. For this, we put box plots on top of the data to display the 5-number summary. The box plot on the left perfectly describes the data, where maximum and minimum, or whiskers, cover all the data points. The right box plot, however, has 3 outliers, which are most likely some machine learning experts, and out of the pure interest of what they earn, we can tag them to see the real values. The violin plots and the means tell us a lot about the distribution, For instance, we can see that the left plot is normally distributed because first, the violin looks symmetric or like a bell, and secondly, the mean sits right on top of the median. In contrast, the right box plot is skewed and does not look like a bell curve, and the mean is far away from the median, which means that the data is not normally distributed, namely, most of the IT people earn similar to the industrial workers, but several of them earn more. Since one of the samples is not normally distributed, we need to compare the medians of these samples instead of the means. So we add the notches and see whether they overlap. They do overlap, but very slightly, so that we need a proper statistical test with a p-value in order to be sure whether the salaries between these groups differ or not. Sometimes it is useful to display some numbers, such as mean and its confidence intervals, so we don't have to guess them by staring at the y-axis. A Wilcoxon test compares the medians of these samples and provides the p-value. In our case, the p-value is small, which means that IT people have a significantly higher salary than industrial workers. In the next video, I'll show you how to easily compute such complex box plots in R in a single line of code, having only 3 arguments, data, x and y, and how to enrich box plots with the results of most useful statistical tests. So stay tuned. But for now, let's summarize all the usefulness of the box plots. First of all, box plots are a powerful data visualization techniques for even small samples of only 5 observations. They are displaying symmetry or distribution of numerical samples. Box plots are non-parametric, so they do not assume normally distributed data. And besides, medians and quartiles are preferred over the mean and standard deviation for asymmetric or outlier-rich data. The box plots can also display summary stats, disparate outliers and confidence intervals, for example, notches for the median and arrow bars for the mean. They also compare and illustrate the statistical difference between groups. And if you ask me if the box plots are perfect, well, I would say almost, because the distribution of the shape is not too detailed, there are no peaks in the violin plot, but other than that, they are almost perfect. If you enjoyed this video and want to see more, feel free to like and subscribe. And as always, thanks for learning.